Hello, y'all. This is Darrell Lee Beverly Jr. back with some linear algebra. I'm going to chapter 3.1, which is a section that I have some homework coming up on soon. So I'll get through that section maybe. We'll see how long it takes. We'll spend about 30 minutes, I guess. And chapter 3.1, and I may revisit chapter 3.2 since I found this cool image in our class site. Showing some more detail about that. But first, I'll start with 3.1, and maybe I'll make a next video reviewing 3.2 again. So let me get the party started. So this chapter is called Vector Spaces, and we'll go to 3.1. So it says, we return now to elaborate on the geometric discussions of solutions of systems of linear equations initiated in chapter 1. Because every solution of a homogeneous system of linear equations is given as a linear, because every solution of a homogeneous system of linear equations is given as a linear combination of vectors, we should view the sets of solutions geometrically as generalizations of lines, planes, and hyperplanes. So I need to write this one down. Right. So we have a homogeneous system, which is the same thing as saying A1 So we have a solution, X. So it's saying every solution of the homogeneous system, let's say because every solution is given as a linear combination of vectors. So let's say that U plus U solves it, and V solves it, and W solves it. That means that U plus V plus W also solves it. All right, so all of these things solve it. That makes sense. To the solution, so I can understand that the vector is this. Let's say 1, 2. Then we could say the solution is like 1, 2. So that's a linear combination of a linear combination of lines, or if they're in R3, then you could have T 1, 2, 3, and each of these vectors would be an R3 cell. Okay. So a line is one-dimensional, plane is two-dimensional. One of the goals of this chapter is to make algebraically precise geometric notion, to make to make algebraically precise the geometric notion of dimension, so that we may assign a dimension to every subspace of Rn. Finally, at the end of this chapter, we shall see that these ideas extend far beyond the realm of Rn to the notion of an abstract vector space. So let's go ahead and go to 1, which is subspaces of Rn. That's why I say we should revisit 3.2 because this probably will help with that. In chapter 1, we learned to write the general solution of a system of linear equations in standard form. One consequence of this procedure is that it enables us to express the solution set of a homogeneous system as the span of a particular set of vectors. The alert reader will realize she learned one way of reversing this process in chapter 1, and we will learn others shortly. However, we should stop and understand that the span of a set of vectors in Rn is a set of solutions of a homogeneous system of linear equations, and the set of solutions of a homogeneous system of linear equations share some salient properties. Trying to highlight salient, but I guess I can't. All right. So definition. Here's the first definition we have. A set V that's an Rn or a subset of Rn. So this symbol means a subset of. So V is a subset of Rn. It's called a subspace of Rn. So that's a subspace. If, I'll say if and only if, one, the zero vector is in that subspace. Okay. Two, whenever a vector is in the subspace V and C is a real number, then C V is in the subspace also. So V is closed under scalar multiplication. And three, whenever V and W are in the subspace, and we have V plus W is in the subspace as well. So it's closed under addition. So I didn't read this chapter. I guess we just covered this in class, but I knew these principles. I just never covered them in the book. We actually had this on the last exam. So closed under scalar and closed under addition. Oh, starting with an example already. Remedial examples. Example 1. A, the trivial subspace consisting of just the zero vector. So 0 is in Rn. You can have as many zeros as you want as a vector. Because a subspace, since 0, of course, is itself, C of 0 is 0, and 0 plus 0 equals 0, which is still in the subspace. B, Rn itself is a subspace of Rn. So Rn is in Rn, makes sense. And C, any line L through the origin to the zero vector in Rn is a subspace of Rn. Remember, the one single loop with no line in the middle is a subspace thereof. If the direction vector of L is U is in Rn, this means that L equals Tu as long as T is a real number. All right, so we have to prove that L is a subspace by checking the three criteria. One, if T equals 0, then the zero vector is a part of the line, because whatever that vector is multiplied by 0, so it'll end up being the zero vector. So V is within the line, and C is a real number. So that means V equals T times U, and T is also a real number. So V equals C Tu, and all I'm doing here is just plugging in what V stands for, equals CTU, which is a scalar multiple of U, hence an element of L, equals TCU. So that's also in a subspace of Rn. All right. So there's closure under 0, closure under which one is this? Scalar. And for addition, V and W are in the line. Thus, V equals SU and W equals TU for some scalars S and T that are real. So V plus W equals SU plus TU equals S plus TU, which is this, scalar of U, which you already know is in the line. And C is a real number, right? D, similarly, any plane through the origin in Rn is a subspace of Rn. We'll leave this to the reader to check, but this is a special case of proposition 1.2 below. And E, so A is in Rn, and A equals not the zero vector. Consider the hyperplane passing through the origin defined by V equals X, which is in Rn, and A dot X equals 0. Recall that A is a normal vector of the hyperplane. We claim that V is a subspace because A is a normal vector. V includes X. As expected, we checked the three criteria. So let's check this one out. So A is a normal vector. V is subspace because it's in the same dimension as X. A dot 0 equals 0. So the 0 vector is in V. If we make X equals 0, all right? So the vector V is in the subspace, and C is a real number. So now we have A dot V or A dot C V equals C A dot V equals C 0 equals 0. So it doesn't seem like they said that. Okay, so little v is in the vector space, and the vector space A is normal to that, right? So since A is normal to that, it has to be normal to any vector in the space. So therefore, it's normal to V, so that equals 0, right? So V, W are in the vector space A dot V plus W equals A dot V plus A dot W equals 0 plus 0 equals 0. Thus V plus W are in V. Thus any vector in V will be perpendicular to the normal in the plane. That makes sense. You have a plane. Doesn't matter how many vectors you draw in that plane, they'll all be perpendicular to the normal of the plane. So that's why we can do this. I got to get used to proofs. I'm not so good at proofs. Example 2. Let's consider a few subsets of R2 that are not subspaces. As we commented on page 93, to show that a multi-part definition fails, we only need to find one of the criteria that does not hold. So A is going to be this. Now we're going to have a blue line going through the coordinate system like this. So S equals x1, x2, which is in R2, and x2 equals 2x1 plus 1. And it says this is not a subspace because all criteria fail. But if we put So I'm not sure the best way to prove this, but I can say that x equals x1 equals the 0 vector. So that would be 0 equals 0 plus 1, and that's not true. So it fails closure under 0. I'm not sure how to do the other ones except to say that right, we'll just keep it rocking. B. So B has this shape. Currently, it's just the axis itself. And all right, the last shape now is this, except this whole area up here is filled in. Right? So this says S equals is an R2 and X1, X2 equals 0. Is not a subspace. So each of the vectors v10 and v01 lies in S, and yet there's some does not. Hmm. Right? Right? So trying to make sense of this. Oh, I see. Because it says x1 times x2 equals 0. So if v equals 1, 0, x1 times x2 equals 0 equals 1 times 0. And uh, w equals 0, 1. X1 times x2 equals 0 because that equals 0 0.1. But v plus w equals 1, 0 plus 0, 1, which equals 1, 1, which equals not 0, 0. Nope, I don't think that's correct. Hold up. Oh, I see. Because that's our new vector. So that becomes our new x1 and x2. So 1 times 1 equals not 0. So it's not a subspace. Right, there's that. So thinking about the first one again. So yeah, so this was a good proof. You can make both of them equal 0, then that's not equal. Or if I make x equal 1 and x2 equals 5, that would have to be 5 equals 2, 1 plus 1 equals 3. So that's not true. And I could think of different ones that I could multiply. Uh, like if I make x1 0 and x2 5 and I scale out of both sides, they're still not going to equal, right? So now let's look at the last one. So this is not a subspace. Because x1, x2 is an R2, x2 is greater than or equal to 0. That's what I'm testing. So if v equals 0, 1, and c is a real number, and we let c equal 5, negative 5, then negative 5v equals negative 5, 0, 1 equals 0, negative 5, and x2 is greater than 0 is not true. So it doesn't pass under scalar, right? So good place to stop. We did about 30 minutes. Have the basic concepts down. What I'll probably do is tomorrow before class, come do some more. My class is at what 5:30. I'm doing a lab in my physics lab, my modern physics lab. We're doing semiconductors. It's not as involved as relativity, I don't think, but still have to see what the data is like. Today we just tried to figure out how to make the circuit work. So I'll see how much I might have to do with the data tomorrow, but sure I'll be able to come on tomorrow sometime before class and continue to build some foundation. And I'll be on throughout the week. If you have any topic uh, request somewhere close around where I'm at in the early parts of the book, let me know. Any questions and comments, put it in the chat, the live chat, or the comments. Help me get 1,000 subscribers. Subscribe, share, and I'll see you all next time.